Here in this video, we're going to talk about confidence intervals of hypothesis test of t-test. And among the three methods of making decisions for hypothesis test, which are critical region, p-value, and confidence interval is my personal favorite because it's easier to understand and it's easier to present. So here what we see is for a two-sided test, this is the confidence interval where this is the upper confidence limit and this is the lower confidence limit. And you can see it's a function of alpha, function of n, and sample standard deviation, all the parameters that you are familiar with. For one-sided test, the upper confidence limit can be calculated this way and lower confidence limit this way. The only difference is here is plus, here is minus. And just to remind you, confidence intervals are basically intervals that contain the population mean with a really high probability, and that really high probability is 1 minus alpha. So alpha of your test is, if it's 0.05, that probability is 95%. That's why it's called 95% confidence interval. So that's the accuracy level of your confidence interval. So for different types of tests, t-test, if it's a two-sided test, you construct a two-sided confidence interval, which was the first one here. If it's a one-sided test of type more than, you got to calculate the lower confidence interval, which was this one. And once you calculate the lower confidence interval, the upper limit is unbounded. Basically, your confidence interval would be, starting at the lower confidence limit, goes all the way to infinity. And if the test is one-sided with less than, then you have to calculate the upper confidence interval, which is essentially this part. That's the part that is upper and lower limit. Well, in that case, your confidence interval will be negative infinity, goes all the way to some upper limit. And once you constructed the confidence interval, how do we make a decision? We reject the null hypothesis if mu naught, your hypothesized mean, is not in the confidence interval. So we're going to apply this on the two examples that we had here. The first example, example 8.6. I'm going to go back to that example to remind you what was that. That was the example on average age of engineering students, and hypotheses were average age is 21 or is not equal to 21. Well, you can see that this is a two-sided test. So we have to calculate a two-sided confidence interval, which is here. So we're going to calculate that for this example. The given information from example 8.6, I'm going to write them down here. X bar, which was the sample average, 22.67. Alpha was 0.05. Mu naught was 21. It was a two-sided test. And sample standard deviation, 4.08. And n was 14. So those parameters we're going to use to construct a confidence interval. The lower confidence limit is x bar minus t of alpha over 2n n minus 1 times s over square root of n. And here is x bar plus. Now, replacing all those parameters in there, you have the x bar, you have the t-value. The t-value of that we want here is going to be t of 0.025 and 13, which we read from the t-table before, and that is 2.16. So this is 2.16 that we're going to use, both here and here. So that will give you, once you do the math and replace all the parameters, you will get 20.3 here and 25 here. Well, that means, and this is a 95% confidence interval because alpha is 0.05, this is a 95% confidence interval. That means with 95% probability, the true population mean is between 20.3 and 25. Well, we were hypothesizing that the population mean is equal to 21. That's what the hypothesis was in that problem. And you can see that here. So since 21 is, in fact, in this interval, right, it's between 20.3 and 25, then we're going to fail to reject the null hypothesis. So since mu naught of 21 is within the confidence interval, fail to reject the null hypothesis. And this conclusion is the same conclusion that we ended up using p-value, and same conclusion that we ended up with using the critical region. So these three methods should give you always the same conclusion. So let's take a look at the second example that we had, example 8.7, and I'm going to go back to that example. This was on mean tensile strength of pins, and the hypothesis was whether mu is equal to 500 or less than 500. And this is a one-sided test of type less than. So looking at the confidence interval formulas, when you have that type of test, you have to calculate the upper confidence interval limit, which is the u, and that is here. So this is the upper confidence limit. So we're going to calculate that here. Again, from that example, all the given information or the derived information that we already calculated is x bar, sample average is 491.3, alpha is 0.1, it is a one-sided test, sample standard deviation or S is 13.2, and N or sample size is 12. And because the alternative hypothesis was mu is less than 500, because of that, we're going to calculate the upper confidence limit, and the lower limit is going to be negative infinity. Upper limit is x bar plus t of alpha and minus 1 times s over square root of n. Again, replacing the numbers in there, x bar is 491.3 plus this t value is t of 0.1 and 11, which we already read from the t table. It's 1.363 times 13.2 over square root of 12. Now, when we calculate that, is 496.5. Well, that means, because alpha is 0.1, this is a 90% confidence interval. So with 90% probability, the true population average is less than 496, right? If you remember in this example, we were testing whether mu is less than 500. So mu naught is 500. Now we just figured that 500 is not in this range. 500 is outside of this range. So therefore, we reject the null hypothesis, since 500, which is the mu naught, is not within the confidence interval. We reject the null hypothesis. We reject the hypothesis that mean tensile strength is equal to 500. So that is the same decision that we ended up using the p-value method and also using the critical region method. So they all give you the same conclusion. But I like the confidence interval better than the other. So here we did the t-test always, and the reason for all these examples was, first, the standard deviation of the population was not known, and second, sample sizes were all less than 30, just like what you see in this example. But whenever you have the choice of doing the z-test, it is preferable to do the z-test because it is more precise, right? Even if we know the population standard deviation, we can still use the t-test instead of z-test, but it's not recommended. Why? Because z-test is more precise than t-test. Confidence interval based on z is tighter than the confidence interval based on t. So if you have a chance of increasing the sample size to more than 30 and do the z-test, that's preferable.